Hello, in this video we'll be talking about bivector potentials in the spacetime algebra. So this is a little bit of a different approach compared to the vector, because if you remember correctly, the gradient of a bivector doesn't yield a bivector. So what this section is going to be is about how you can reduce the problem to just looking at bivectors. So first we look at the relative fields A and C present in AE and AM. So if you recall correctly, these AEs and AMs, they come from the vector potential right here, the complex vector potential. And the A is the part of the AE, and the C is part of AM. So the relative fields present in these vectors can be broken, Sorry, just muting myself because I was sneezing. Can be broken into relatively transverse and longitudinal. Longitudinal components. So you can break A and C into longitudinal components and transverse. So A, this, plus A perpendicular, C parallel, C perpendicular. Now, they are talking about transverse and longitudinal rather than perpendicular and parallel, but the concepts here are essentially the same thing. You just call a field when it propagates longitudinal if the arrows propagate in the direction of the field of motion, and then transverse if they propagate perpendicular. So for example, if you had an electric field, like the traditional view of an electric field, where it's propagating in this direction, so k hat, then the electric field here goes like this, and this is called a transverse field. So transverse, because the direction of motion is this way, but the field points out in this direction. So that's what it's saying for these potentials, is that the potential A has a component going in the direction of propagation and a direction, and one going perpendicular to the direction of propagation. So transverse, longitudinal. Oh, and then you define these things such that the divergence, the 3 divergence of A parallel, or sorry, no, A perpendicular, is equal to the divergence of C perpendicular, which is equal to 0, and the curl, 3 curl, of A parallel is equal to the 3 curl of C parallel. Oh, I meant to put curl here, which is equal to 0. So what this means is that these fields these fields don't diverge, so they just essentially remain as changing about this axis, but they're not there's no field lines leaving. The field lines kind of rotate around the propagation direction, whereas this is saying that there is, for the parallel fields, there is no rotation about that. There is only field lines leaving or going in. Or there are only. Bad grammar. So this means if you take this means for a gauge field G, where this G is equal to GE plus GM I gamma naught. This is the relative frame version of this complex vector. So for this gauge field, Z prime, which is the new, this is the new field, so is the old complex vector field, plus divergence of G. Okay, yeah. This implies that, sorry, I started thinking about something else. This implies that Z prime gamma naught is equal to Z gamma naught plus gradient of G gamma naught. So let's move this down here. And then we can expand this out, so we get AE gamma naught minus AM gamma naught I. There's a minus sign here because this gamma naught commutes with the pseudoscalar, plus gradient of G gamma naught. We'll expand this out near the end, and this is equal to expanding out AE FE plus A, and then minus FM plus C I, and then the gammas here cancel out with the gammas here, because when you commute the gamma over to the right, this becomes a positive sign. Keep having to pause to sneeze. My nose is really being crazy right now. So you can rearrange it to that. Then you still have this gauge field here. Okay, so I think before I made this assumption that this is a complex vector, but it's not. This is just a complex scalar. My bad. So then we have this, which then equals phi e plus a minus phi m I minus c. Oh, okay. So my bad. I was just accidentally started repeating the last line. So you end up with the same. You can break these into the longitudinal and transverse components. So minus phi m I minus c perpendicular minus c, or parallel c perp, and then plus g gamma naught. And this, you can call this as z parallel gamma naught plus z perpendicular gamma naught plus divergence of g gamma naught, which you can just call z prime parallel gamma naught plus z prime perpendicular gamma naught. And what are these terms exactly? We can say, but this implies that z prime of parallel gamma naught is equal to z parallel gamma naught, the original, plus the gradient of g gamma naught, which is equal to phi e plus partial change in time of ge plus a parallel minus g e, and then minus phi m plus partial time of gm I, then minus c parallel minus, oh, and these are three gradients, gm I. So you end up with the longitudinal components and also with the gauge components. Similarly, you have that z prime perpendicular is just equal to z perpendicular gamma naught, which is just equal to a minus c I, and these are the perpendicular components, the transverse components. So you see that under a gauge transformation, this complex vector field remains the same in the transverse direction and only changes in the longitudinal direction. So essentially, this is gauge invariant. So I can say, and thus z perpendicular gamma naught is gauge invariant. So I can look at this. So this Z perpendicular gamma naught is gauge invariant. Now what is done is to call capital Z equal to Z perpendicular gamma naught, the transverse bivector potential. And there's another one, call C equal to Z prime parallel gamma naught, the even potential. Now, in the text, they call this the spinor potential. However, as I said, their definition of spinor does not agree with the academic definition of spinor as a minimal left ideal. So, because this is just an element of the even subalgebra, I'm just going to call it the even potential, because the spinor potential is misleading. So then, if you call these two things, if you define these two things, then you can say that F, the bivector field, is equal to the gradient of Z, as what we talked about last, is equal to gradient of, if you expand out Z, you get Z parallel, or we're going to talk about this with a gauge transformation, so you get Z plus some gauge transformation. It is equal to Z parallel G naught, or gamma naught, plus the gauge here, gamma naught, and then plus Z perpendicular gamma naught. You have a gamma naught out here, and then if I fix the fact that I'm starting to write in a downward slope, then you have that this right here is just your Z prime parallel, or Z prime parallel gamma naught, plus Z perpendicular gamma naught. So you have this, which is equal to the gradient of, you have C plus capital Z gamma naught, which of course is, this is how the problem can be reduced to a bivector potential, where you have, this is an even potential, so it has scalar and bivector components, and this has, what's it called? This has only bivector components. And this implies that the gradient of f, which we know is 0, becomes the Laplacian of, or the D'Alembert of C plus Z gamma naught equal to 0. So you can therefore look at these potentials. So you can actually choose a gauge here in C, because C is defined as gauge dependent. So you can define a gauge that will make C equal to 0. So let's choose a gauge that does that. Let's choose a gauge such that C is equal to 0. So the first bit is, well, if we want this to go to 0, then we need to have that the partial with respect to time of GE is equal to negative FE, or phi. So we get partial not GE is equal to negative phi E. Likewise, we get that this is equal to negative that. So partial time GM is equal to negative phi M. And then we can choose that these are equal to each other, and likewise that these are equal to each other. So we can just write 3 gradient of GE equals a parallel, and the 3 gradient of GM equals C parallel or longitudinal. So you get these 4 conditions, which then imply, so therefore C equals 0. So choosing these gauges here makes this disappear. So this disappears, which means this disappears. So I'm going to write a better S. So you end up with the gradient of F is being equal to the Laplacian of capital Z gamma naught, which is equal to 0. But gamma naught isn't going to actually impact the dynamics of this Z. This will not impact the dynamics of the bivector. So this means we effectively need to look at only the D'Alembert of Z equal to 0 to determine dynamics. So because we choose a gauge equal to 0, then we effectively only need to look at this change of the bivector potential to see what's going to happen for F. But how, let's see, but how is this related to actual fields? How is this related to actual fields? That is, how can we relate this Z to equations so that we solve for this and then we plug in the values for this into those equations, or to solve for the electric and magnetic fields? Well, it's actually pretty simple. First, you have f is equal to the gradient of capital Z gamma naught, which is equal to the gradient of Z perpendicular and gamma naught squared, which is equal to gradient Z perpendicular, which is equal to the gradient of A. Here, if you break these into, and then if you break these both into relative frames, you get partial naught minus, so you get this, and then you also get, so you get a gamma naught here, and then you get a gamma naught here for A. Let me think about this. Yeah, you get a negative A perpendicular and a negative C perpendicular. And these square, so the negative sign here comes from the fact that gamma was defined, where is it? It's up here. Yeah, so the fact that gamma here is, or this is y, so gamma here is on the left, but you have a negative A. Gamma here is on the left, you have a negative C. So here you have negative A, negative C. So you have this, which is equal, if you expand this out, you end up with partial naught minus partial naught A perpendicular, then minus partial naught C perpendicular, then plus this A perpendicular, which this is just equal to the curl of A because of the definition up here. Because the dot, the divergence of the transverse field is equal to 0, so we know that it must be equal to the curl, but the curl always has an I here, so we have this as being the curl. Then we have a plus curl of C perpendicular, I squared goes away, you get a negative sign. So this equals that. We can then say that we have negative partial of A perpendicular minus the curl of C, and then plus minus time a partial of C perpendicular, or transverse, plus curl of A perpendicular, and then an I right here. So we know that this is, so we can say, but F equals E plus B I. And we have something of the same form. We have something and then something I, which means that we can equate like terms. So this implies that E is equal to this, and B is equal to this. So these are the final equations that can relate the bivector potential to the actual electric and magnetic fields. And you'll notice that these actually look a lot like like Maxwell's equations, where, recall, you have what was it? You have partial change in time of, so yeah, for Maxwell's equations, you have 1 over c change of B is equal to curl of E. If I recall correctly, you have this equation, which would mean that you would have this, so plus, minus. So you'd have these equations. So these look suspiciously like Maxwell's equations in vacuum. And that's just because of the geometry of spacetime, because this is just the way that bivectors change. So if we define a potential based off of bivectors, then this is the way bivectors change. So it's just because of the geometry. They look exactly like Maxwell's equations. So I have this.